All right, my friends, let's take a quick look at the year in mechanics. We began by looking at motion. Here is a projectile being launched at a 25-degree angle from the horizontal from a cliff. And let's look at the acceleration, velocity, and position both horizontally and vertically. Well, horizontally, there wouldn't be any acceleration because there wouldn't be any horizontal forces except maybe air drag, but we'll ignore it here. If you're not accelerating horizontally, then your velocity would stay constant. So the initial horizontal velocity it would be given, which would be 8 cos 25, that would be constant. Well, if you have constant velocity, your position grows at a constant rate. So there's x versus t. In the y direction, it's accelerating because of gravity the entire time. So you have a constant acceleration of 9.8 meters per second squared downward. And so with a constant acceleration, your velocity is going to change at a constant rate. Notice that it starts positive because the ball was going up initially. The velocity happens to cross through zero. That's at the peak. But nothing really special about that point except for the velocity happens to go to zero. The acceleration just stays the same throughout. And then it starts to gain negative velocity as it comes back down. And then your y coordinate as a function of position is going to be curved like this, going up while the velocity is positive, crossing zero at its maximum height, the velocity crosses zero, and then it starts to get steeper and steeper coming down as it gains more and more downward velocity. Then we're asked where the ball is going to land. Well, the key here is you separate the vertical and horizontal motion. So vertically, we have a constant acceleration, so we're able to use kinematics. Horizontally, we also have a constant acceleration, just happens to be zero, so we can also use kinematics. The key is to keep them separate. So vertically, we can use this kinematic equation and plug in delta y of negative 10, because I chose positive up, so delta y is negative 10. Acceleration would be negative 10, again, only because I chose positive up. And your initial vertical velocity here would be positive. And then you would just solve this quadratic for the time of flight. And then what we can do then is look at the horizontal motion. Horizontally is really simple. It's just distance is rate times time because there's no acceleration. And now that we have the time of flight, we can just multiply the horizontal velocity times that time of flight. And that's how far it will go. The only thing people really screw up on this stuff is, well, do not use a final velocity of zero here because the projectile kinematics pertain to the flight, not to the impact. The kinematic equations work for stages of motion where the acceleration is constant. All right, next we looked at situations where we might need calculus to handle motion. So what we have here, it says a 2-kilogram object starts at the location x equals 4 meters and moves with this velocity function v of t is 3t squared minus 4t. And first we're asked to find the force on this object. Well, since the velocity is changing with time, there is an acceleration. And since we know F equals ma, we can figure out what that acceleration is by looking at the change in velocity. So from F equals ma, a is the time derivative of velocity. So let's just take the derivative of that velocity function. It would be 6t minus 4, and then multiply it by the mass. And so this function here would be ma, and then you would just check it at t equals 2 in order to find the force on the object at t equals 2 seconds, and it would be 16 newtons. Then we're supposed to find the position at t equals 2 seconds. The key here is don't use some formula for delta x just because it says position. You can't use constant acceleration kinematics here. You do not have a constant acceleration, so you're going to have to use calculus to kind of make your own kinematic equation. Well, so what we want to do is our position function is going to be the antiderivative of this velocity function, right? So you pump the power on the t up, the t squared term becomes a t cubed. And then minus, 2t squared for this term. And then you'd have an arbitrary constant from the antiderivative, but the arbitrary constant would just be the initial position because we know that x of 0 equals 4, so that's where that comes from. And if we check this function at 2 seconds, we're still at 4 meters. So it turns out the object kind of went away, but then came right back. To find the momentum of the object, well, that's just mass times velocity. So if you just take your velocity function, that we're given and multiply it by the mass, then that would be your momentum function. And then you would just check it at t equals 2 seconds, and that would be the momentum of the object at that time. Finally, we're asked to find the rate of change of momentum. Well, here we have this time-dependent momentum function. So let's just take the derivative of that momentum function. So the momentum function would be 6t squared minus 8t, and then just take the derivative of that function, 12t minus 8. this would be the rate of change of momentum at any time. And if we check it at t equals 2 seconds, you'd get 16. Now, that's no accident. That is the same answer that we got when we found the force, because the rate of change of momentum is the force. And so that's why we got 16 newtons for the force at 2 seconds, and also the rate of change of momentum was 16 at t equals 2 seconds. All right, next let's look at a collision. We're going to use the concept of momentum because momentum will be conserved when forces are only between objects within a system. There's no external forces. So here we have a system of two objects, a 2 kilogram and a 6, and they're just going to bonk into each other here. And what we're supposed to do is find the speed and direction of motion of the 6 kilogram ball after the crash. Well, the key here is you don't want to conserve KE across the crash, because what's going to happen is some of that energy is going to get lost in the form of heat and sound to the environment. So the go-to concept here is conserving momentum. So you can conserve it independently in the vertical and horizontal directions. So vertically, we have no vertical momentum before the crash. So that means we're going to have none after. Well, so if you look at the momentum after, you're going to have momentum, vertical momentum here of 6, 2 times 3 would make 6, times the sine of 20. That would be the vertical momentum of the 2 kilogram ball. And then the vertical momentum of the 6 kilogram ball would be some value py actually pointing downward. Well, so these two things must be equal and opposite. And so we just learned the downward momentum of the 6 kilogram ball after the crash. It's 2.05. Now let's look horizontally. P before is P after. So before the collision, we had a momentum of, 8 units, 2 times 4 before the crash. Well, that means the two horizontal momenta that are present in the system after must add to 8. So we have 6 cos 20, which would be the rightward momentum of the 2 kilogram ball. And then Px is what I'm calling the rightward momentum of the 6 kilogram ball. Well, solving for Px, we get 2.36. So now we know both the downward and rightward momentum of the 6 kilogram ball. Well, since we know the rightward momentum is 2.36 and the downward is 2.05, that allows us to calculate this angle below the horizontal that the 6 kilogram ball will have. And it turns out it's like 41 degrees, below the horizon, I guess, or I called it south of east here. And then we can also use the Pythagorean theorem to find the net momentum, since we know the x and the y. And then finally, we're asked how much energy, if any, was lost or gained in the collision. We'll define the energy that was present before, just 1/2 mv squared, 1/2 2 times 4 squared. There was 16 joules present in the system before. Well, if we now handle 1/2 mv squared after the collision for the two objects, you find that there is less energy present in the system. And so what that means is 6.2 joules was lost, likely to sound and heat. And so again, that is why we don't try to conserve kinetic energy across the crash. So that's a bit of a mechanics felony to try to conserve the energy across collision, most of which are not elastic. And so that means some kinetic energy will be lost to the environment. Next, let's look at torque and moment of inertia. It says this stick's 3 meters long, has a mass of 2 kilograms. Looks like there's an axis here and somebody's pushing on it. First, we're supposed to find direction and magnitude of the torque. Well, since the axis is here, it's getting pushed here. Torque is force times distance from the axis. And so you have a 6 Newton force acting at a distance of 2 meters from the axis, since this is a 3 meter stick. And so you have a 12 Newton meter torque. And the reason I said it's out of page is you have this counterclockwise sense of rotation. So by right-hand rule, people will tend to say that that's out of page. You could get away with saying counterclockwise in this particular case. Moment of inertia. What I did here was you would use the moment of inertia of a stick about the center, which would be 1/12 ml squared. But then what's happened is the center would be located at 1.5 meters, but our axis is actually off center. It's 0.5 meters off axis. So you have the second term that's like a shift of the axis from the center. This md squared term, you're basically treating like the object like a point mass that's just been shifted by a distance d. So you have the moment of inertia about the center, 1/12 ml squared plus a shift of md squared, and that gets you a moment of inertia of 2 kilogram times meter squared. Finally, we're supposed to find the angular acceleration of the stick if it gets pushed like this. Well, that's going to be a case where you want to use the rotational version of F equals ma. We're going to use the angular version of F equals ma. So rotational force or torque equals rotational mass or moment of inertia times rotational acceleration or alpha. Well, our torque we already calculated to be 12. A moment of inertia was 2. And so what we learn is that this thing is going to have an angular acceleration of 6 radians per second squared. And again, you could give a sense of direction of out of the page or counterclockwise. And then finally, it asks how many rotations would this make in 6 seconds. That's the rotational equivalent of asking how far did it go. So you're going to do rotational kinematics. So instead of looking for delta x, we're looking for delta theta, because you're kind of looking for like how much did it turn. So you're just going to run a kinematic equation here. I'll assume no initial angular velocity here, and so you'd have rotational version of 1/2 at squared, which is 1/2 alpha t squared. And you'll find that it goes 108 radians, which if you divide that by 2 pi, you'll learn that it goes 17.2 rotations in that time. So we have a situation here where a block is going to slide down a hill, and then it's going to hit a rough patch, and then it's going to hit a spring. So first we're asked, find the speed of the block before it gets to the rough patch. So it's just sliding down a hill. Well, a good way to handle that is to say the energy before equals the energy after. There's no mechanism on a frictionless surface for it to kind of lose mechanical energy. So the energy it's got before is gravitational potential, mgh. The energy it would have after, meaning right before it got to the rough patch, would be all kinetic, energy of motion, 1/2 mv squared. So you'd see the masses cancel, and we can figure out how fast it's going that way. So we'd be starting at 0 meters per second, and then say getting up to 7.75 meter per second before the rough patch. Now on the rough patch, friction is going to act on it as it slides across, and work done by friction is going to be friction force times distance. Well, so friction force would be the coefficient of kinetic friction times normal force, which would just be mg in this case. And so what you would learn here is that 48 joules of work would be done by friction against the object, I guess, negative work of 48 joules. And so then what we're supposed to do is get the speed after the rough patch. And the concept I like to use there is you'd say, well, E before is E after plus any that got wasted. So right, the E after will be a little bit less because some's going to get wasted. Well, in fact, exactly 48 joules is going to get wasted. Well, so what I did here is I took the before state of the system to be when it's at the top. The after state is after the rough patch. So 1/2 mv squared, where v would be the speed after the rough patch. And then E wasted we already found to be 48 joules because that was the work done by friction was negative 48 joules. And so if we do that, we learn that the thing would only be going 6 meters per second, which makes sense because it was going 7.75 before the rough patch, so it should be going a little slower after. Then finally, we're supposed to find the maximum distance the spring's going to compress. I would again handle like E before is E after, but you want to be careful that the E before, let's take it as the kinetic energy before it hits the spring. So what we're going to do I say, well, how much energy does it have before it hits the spring? Well, it had 120 at the top here, but then it lost 48 joules sliding across the patch. So it's only got 72 joules left before hitting the spring, and that is in the form of kinetic energy. Well, that's going to become spring potential energy when it mushes the spring. And so you'd set that equal to 1/2 k delta x squared, and what we learn is that spring gets mushed by about 0.6 meters. All right, next let's take a look at what happens after it hits that spring. Going to oscillate. So we'll say it hits the spring and then it sticks. So what, it's going to come in at 6 meters per second and it's going to hit that spring and start to bounce. So what we're supposed to do first is get the period of oscillation for a mass on a spring. Well, that's just 2 pi root m over k. So m being the mass, 4, k being the spring constant, we'll say it's 400. So that's just a little bit of a plug and chug, and it would take, pi over 5 seconds to bounce back and forth one time, which would be the period of oscillation. As far as the position of this thing as a function of time, you'll see on your little formula sheet, you could write it as a cosine of a frequency times time. I'm choosing sine here because we know that when this thing hits the spring, it's going to squish the spring in, but then it would like rebound out beyond the position where it hit the spring. So it's sort of starting in the middle of the sine wave or cosine wave. Well, so since it starts in the middle of the oscillation, not at either the max compression or max extension, it's convenient to just choose the sine. So you'd have amplitude sine root k over mt. And we found the amplitude was going to be 0.6 from the last problem because that's how far it was going to squish the spring in from this unstretched and uncompressed location. And then finally, we're supposed to find the velocity 1 second after it hits. Well, this is the position as a function of time. So to get the velocity, we just need to take the time derivative, dx dt. Well, that sine will become a cosine if you take the derivative, and the 10 will pop out because of chain rule. So you're going to end up with 6 cosine of 10t. 10 times 0.6 is 6. And then what we want to do is we're supposed to find it exactly 1 second after. So you'd plug in 1 for t. And then just make sure you're in units of radians on your calculator. And 1 second after it hit, this thing would be going, say, 5.3 meters per second going backward or to the left. Kinetic energy and torque. What we've got here is a block that's attached by a rope to a little drum that's just going to unwind and unspool this thing as it falls. And first what we're supposed to do is says use energy to find the speed of this 2 kilogram thing after it's fallen a meter. Again, the concept that what I like to do is think about it as E before is E after plus anything that gets wasted, although we don't really have a mechanism for wasting energy here, so we're just going to say E before is E after. And before, meaning when the block is up high, you just have the potential energy of the block present in the system. We'll call it mass M1GH. And then afterwards, you got 2 types of kinetic energy. The block is going to be translating downward, so it's going to be moving, 1/2 M1V squared. And then this little drum is going to be rotating, so it has rotational kinetic energy, 1/2 rotational mass times rotational velocity squared. And so then it's just a matter of plugging and chugging a bit, although you do have to watch out for, you'd sort of have 2 unknowns. You'd have the velocity and the angular velocity. But as long as this rope isn't slipping, then as the drum rotates around once, exactly 1 circumference comes out of worth of rope. And if that's true, then V equals R omega, the velocity of a point on the rim would match the velocity of the 2 kilogram block downward. So you could make the substitution V equals R omega, and then that would remove that omega as an unknown and sort of reformat it as a V. Now V, the speed of the block after it's fallen 1 meter, if we plug in H equals 1, would be the only unknown. So now we can just send it, and you end up getting 2.39 meters per second for the speed. Next, we're supposed to do the same problem by using F equals ma on the mass, and torque equals I alpha on the disk. So let's look at how that would play out. If you do F equals ma on the mass, you'd have M1g, gravity downward, and I'm going to call that the positive direction since it's moving down, and tension force upward or in the negative direction, so M1g minus T is M1a. That's all you could really learn from doing forces on the 2 kilogram object. Then I would look at torque as I alpha on the disk. Well, torque is just going to be torque about the axis, about where it's rotating. Would be tension force times radius, and then that's going to be equal to the moment of inertia of the disk, 1/2 mr squared. And then here I'm going to make a substitution since it's not slipping. A equals R alpha, or alpha is A over R. And so now I have a relationship between tension and acceleration, which I also added a relationship between tension and acceleration when I was working with forces. So I have 2 equations for 2 unknowns, and you can then substitute this expression in for the tension, and then the only unknown would be the acceleration. So if I do that, putting 1/2 m2a in for the tension, I can solve for a, and it's allegedly 2.86 meter per second squared. And then what I can do is it has a constant acceleration of 2.86 meters per second squared, so I can now just run a kinematics problem to see how fast something would be going after it had fallen or gone 1 meter with that constant acceleration. So I'm going to use this kinematic equation, and what I find is I also get 2.39 meters per second, which of course I should get the same answer since both the energy approach and the forces and torques approaches are valid. Next, let's look at gravitational potential energy a bit in orbits. You get this potential energy expression minus Gm1m2 over r, which basically you can get from knowing force is negative slope of the PE, and if you know what the gravitational force is, so force is negative derivative of the PE. What we're supposed to do now is find the speed that you must give an object to launch it to a distance r above the surface. So we're going to launch it from the surface of the planet up to a position where it's actually 2r away from the middle. So we're going to double its distance, let's say, from the center of the planet. Well, so let's do E before is E after. Before being right when we launch it, and after being when it's way up high. So before, it's going to have two types of energy. 1/2 mv initial squared, because that's the v initial is the speed we're going to launch it with. And it's going to have gravitational potential energy with a distance associated just with the radius of the planet. So it's got kinetic energy and it's got gravitational potential because it's at this location on the surface of the planet. Afterward, well, that's going to be when the ball's at its max height. So it's not going to have KE anymore because it's going to go up there, turn around, and then want to fall back down. So at the turnaround point, no kinetic energy. All it has is gravitational potential, but your new height now above the center of the planet is 2r. So instead of r, it's now 2r. Well, so now the only unknown in the problem, I guess, is v initial, and so then we can solve for it, and you would get this expression for how fast you'd have to shoot the ball to get it to go that far above the surface. Sometimes they ask people about escape velocity. In that case, what you'd do is this 2r, the final position of this thing, what you'd do is you'd set that to infinity, so the right-hand side of this equation would be 0 if you were asked about escape velocity, which we were not here. Second part of this, find the speed that an object must have in order to orbit at that height, in order to be in a circular orbit at that height. That, what you want to remember is just do F equals ma, where it's going to be accelerating because it's going in a circle. And so the centripetal acceleration is v squared over the radius of that circle. Well, so let's check this out. Gravitational force, gmm over r squared. But the r of the orbit, be careful, the r is going to be 2r because it's orbiting way out here. And then likewise, for ma, we'd have mv squared over the radius of the orbit, but the radius of the orbit, again, is going to be 2r. So just be careful that you're thinking about the right distances there. And then finally, we can solve for the velocity that it would have if it were in a circular orbit out there, and it would need to orbit at this particular speed. Let's look at a collision that produces a rotation. What we've got here is a ball going 50 meters per second at this funny angle, and what it's going to do is hit and stick to this disk, which is actually free to rotate about this axis that's labeled here with an X. And it says, find the angular velocity of the system after the collision. This is a collision, so what we want to do is conserve angular momentum. Don't attempt to conserve energy, because what's going to happen is this thing's going to go donk when it hits. It's going to release a bunch of kinetic energy into the environment. So it's like a physics felony to try to conserve the energy across the collision when it's not specifically mentioned somehow that it's going to be elastic. So we have angular momentum before is angular momentum after. The ball carries angular momentum on the way in. So a way to write angular momentum of a object that's just traveling in a straight line is, you could write it as mv perp r or mv r perp, and then afterwards the ball and the disk are going to rotate. So I'm going to use this expression as I total omega for the angular momentum after. Well, so let's just sort of plug in here. Afterwards, the moment of inertia would be the moment of inertia of the ball plus the moment of inertia of the disk. The ball will treat as a point mass, mr squared. The disk, moment of inertia of a disk is 1/2 mass of the disk times r squared. It's a good idea to call mass of the disk like md and then maybe reserve the m for the ball. So don't be lazy and just put m's for everything. And what we should now be able to do is kind of plug and chug. The v perp, the component that we need of the velocity, is actually just this, I guess, vertical on this, or not vertical, toward the top of the screen. So it would be like 50 sine 40. We want to pull out the component of this velocity vector that points toward the top of the screen, not the component that points directly in toward the axis, because then that doesn't lead to rotation. And so what you find when you plug in here is it goes 18.4 radians per second after the crash. Next, we're supposed to figure out if energy is gained or lost. Well, the energy before would just be the kinetic energy of the ball, 1/2 mv squared. Looks like the ball comes in with 2,500 joules. Afterwards, we would have, well, everything's rotating, so we can say it has rotational KE of 1/2 rotational mass times rotational velocity squared. And plugging in, you find that you only have 296 joules after the collision. So 2,500 joules coming in, and then only 296 remaining after the collision. So a lot of energy was released to sort of heat and sound thunk when this ball hit. And so there was 2,204 joules looks like were lost. At risk of being repetitive here, the key is to realize in the problem like this, do not attempt to conserve kinetic energy across the collision. Some of the joules that are brought in by this ball are going to be, lost to the environment as heat and sound. So a mistake that students will make sometimes is they'll try to say that the kinetic energy of the ball all becomes rotational kinetic energy of the system, and that's not a good way to handle this. All right, finally, we're going to take a look at drag forces. An example would be air friction. Drag forces tend to depend on velocity in some way. Here we're going to look at one that's just linear in velocity. So here we have a rocket car that has a thrust force F sub t, and an air drag force that's proportional to velocity. And the rocket's going to start from rest at x equals 0. Rocket will turn on, it'll take off, and drag will start acting on it. What we're asked to do first is find its terminal velocity in terms of quantities in the picture. Well, if something's moving at terminal velocity, it is not accelerating. And so that means forces on it will balance because it would accelerate if they didn't. And so we can now solve for Vt by just setting the force accelerating it to the right equal to the force that's sort of working against it. Next, we're supposed to find the velocity as a function of time. Here you want to begin with the F equals ma. And where we can get velocity involved is, well, the sum of the forces are the thrust force acting to the right, so I'm calling that a positive force, kV acting to the left, so it's negative, and then set it equal to ma, but here we substitute a as dv dt. So here we get a differential equation for v. You'll also see differential equations when in the context of oscillations, but air motion with drag is a context where you'll also see differential equation. The first move I tend to make, it's just stylistic, but I tend to try to get clear the coefficient on the v. So what I did was I divided through by minus k every term. And then we need to separate and integrate. So what I do is I bring the entire left-hand side under the dv, and everything else goes onto the left. So I brought the v minus ft over k underneath the dv, and I put minus k over m, or minus k over m dt on the left. You start your stopwatch at t equals 0, end at t. The thing started with no velocity and is going to move at some arbitrary velocity. So now we just need to integrate both sides. When you do that and work through the rest of the math, you find that you get a velocity that approaches ft over k, which kind of makes sense when you have a terminal velocity of ft over k. And then finally, we're asked at what time does the velocity equal half of v terminal? All we have to do is set this expression itself equal to half of v terminal, or set it equal to ft over 2k. And then finally, it's just an algebra problem to solve for the time, and that will let you know the time at which it's traveling half of the terminal velocity. Also, thanks for checking this out. I hope it was a helpful review of AP Physics C for you.